Last session of today. The first speaker is Miguel Ángel Mota from Mexico, and will speak on symmetries.
Thanks for this wonderful invitation. Let me start with a historical introduction. Well, as you probably know, the method of side condition was invented by Stevo Todorcevic, and it describes a style of forcing in which elementary substructures are included in the conditions of a force imposed in order to ensure properness, and therefore in order to preserve omega 1. Let me recall some basic definitions. If we have a poset and a condition Q living in P, and we have a countable elementary substructure of H theta, then we say that Q is said to be NP generic if and only if Q forces that the generic filter, well, I'm going to give this definition. If and only if for every dense subset D of P belonging to N, the intersection N is predense below Q, which means that the generic filter, any generic filter containing Q, is going to intersect the intersection N. And something stronger is this second definition, thus that Q is said to be strongly NP generic if and only for every dense subset D of P intersection N, D is predense below Q. And of course, 2 implies 1. That's because by elementarity, if D is a dense subset of P and D and P, they are both elements of N, or they are both definable in N, then D intersection N is a dense subset of P intersection N. So if P is in N, then 2 implies 1. Or if P is definable in N, then 2 implies 1. The second remark is that if Q is strongly NP generic, then Q forces that N intersection G is a V generic filter on the countable set N intersection P, and therefore we're essentially coding a coherent real. So Q adds a coherent real. A typical condition of a forcing P equipped with a side condition is a pair XA, where X is an approximation to the desired generic object, and A is a finite set of countable elementary substructures, such that if N is in A, then the pair XA is NP generic. And Friedman and Mitchell independently took the first step in generalizing this method from adding generic objects of size omega 1 to adding larger objects by defining forcing posets with finite conditions for adding a club subset of omega 2. And it was Niemann, the first one, to simplify the side conditions of Friedman and Mitchell by presenting a general framework for forcing on omega 2 with side conditions. Both the forcing posets of Friedman, Mitchell, and Niemann for adding a club of omega 2 with finite conditions, they all force that the continuum is equal to omega 2. And that's because, in fact, all these forcings, they can be factored in many ways, so that the quotient forcing also has strongly generic conditions in the intermediate extensions. So Friedman asked in 2005, I guess, whether it's possible to add a club subset of omega 2 with finite conditions while preserving CH. And together with John Kruger, I solved this problem by defining a forcing poset which adds a club to a fat stationary set and falls in the class of coherent adequate type forcings. We proved that, of course, any coherent adequate forcing preserves CH, and moreover, we have something stronger. Any coherent adequate forcing on H lambda, that means that our side conditions are countable elementary substructures of H lambda, collapses 2 to the omega to have size omega 1, but it preserves the successor of 2 to the omega and forces CH. This is the content of the first part of my talk. Probably I'm very optimistic. In part 2, I will explain my recent, I will try to explain my recent work with William Weiss from the University of Toronto. And in this case, we solve a well-known problem in the theory of compact scatter spaces and superatomic Boolean algebras by showing that under GCH and for each regular cardinal kappa greater or equal than omega, there is a posed p kappa preserving all cardinals and forcing the existence of a kappa thin, very tall, locally compact Hausdorff scatter space. And our result, of course, generalizes that of Baumgartner-Scheller for kappa equals to omega. And for kappa strictly above, for kappa bigger than omega, we designed the posed p kappa as a higher analog of the posed p omega, originally introduced by Aspero and Bagaria in the context of an unpublished alternative consistency proof from 2000. That proof is from September 2009, I guess. And what's the connection between this? Oh shit! Oh, sorry. What's the connection between these two parts? The connection between these two parts is a set theoretical notion of symmetry that I will explain throughout this talk. Let me start with the first part of the talk. I'm going to start explaining the notion of coherent adequate sets. This development is due to Kruger. From now on, we assume that lambda is a cardinal which is at least omega 2. It's a fixed cardinal of uncountable cofinality. And also, we fix a predicate which we assume that calls a well ordering of H lambda. Let X be the set of all countable elementary substructures of this H lambda together with the membership, together with this additional predicate. And let gamma be the set of all ordinals in omega 2 having uncountable cofinality. So if n is in X, then n is of course an element of H lambda. That's simply because lambda is of uncountable cofinality, and gamma is definable in n. Now we introduce a way to compare members of X for M in X. For one of these structures, gamma n denotes the set of those betas having uncountable cofinality, such that beta is the minimum gamma is the minimum of gamma minus the supremum of M intersection beta. I can give an alternative definition, but wait a minute. So for every beta in gamma M, there are no ordinals of uncountable cofinality in the open interval supremum of M intersection beta beta, because remember that this is the minimum. This is the minimum gamma minus the supremum of M intersection beta. In particular, omega 1 is in gamma M, and since M is countable, the cardinality of gamma M is also countable, and gamma M is included in gamma N if M is included in N. If you have two of these structures, then you can define the maximum of gamma N intersection gamma N. And the main property here is that if M prime denotes all those ordinals of M intersection omega 2 together with those limit points of M, the limit points coming from M intersection omega 2, then M prime intersection M prime is included in beta Mn. And also, gamma M can be described as the set of all those ordinals beta, such that beta is of the form gamma plus omega 1, where alpha is
Sorry, could you
We don't see any.
Yeah, could you use a different color chalk?
White chalk.
wait a minute, please.
You're using what? Yeah.
Okay, white. So gamma M is the set of all those ordinals beta, such that beta is of the form alpha plus omega 1, where alpha is in M prime. This is not difficult to prove this equality. And yeah. And now we define two relations. We define the relation of being of less than and equivalent on X. And we say that M is below N if M intersection, the comparison point of M and N is in N, implying that this beta Mn is in N. This is simply because beta Mn is defined as this minimum, and gamma is definable in X, and therefore is definable in all these elementary substructures living in X. And we say that M and N are equivalent if M intersection the comparison point is equal to N intersection the comparison point. And then we say that M is less than or equal to N if either M is below N or M is equivalent to N. And of course, since the comparison point is above omega 1, then if M is below N, then that implies that M intersection omega 1 is below N intersection omega 1. And if they are equivalent, that implies that they have the same height with respect to omega 1.
Sorry, can I ask you to go back just quickly
Of course.
to the definition of, I missed the definition of beta.
Which one?
This definition of beta Mn. Okay.
Yeah, that's the maximum of gamma M intersection gamma N. And we say that a subset A of X, a subset of, recall that this is a subset of elementary substructures. They are elementary substructures with respect to the membership and with respect to the additional predicate Y. And a subset A of X is adequate if and only if every two elements of A are comparable under this relation. And note that if A is finite and adequate, N is in X. Okay, so this is the situation. Where is the eraser? Sorry. Yeah. So imagine that we have a subset set consisting of adequate structures, and this subset lives in N. A is finite, so N has access to all the elements of A, and therefore it has access to all the initial elements of each element of A. Therefore, A together with N, this is also an adequate set.
Is that a, you mean on N where you write A is in chi?
Know that if A is finite and adequate, N is in X. A is probably I should say here that A is a subset of yes, A is a subset of X. Is finite and adequate, yes. Then N has access to all the initial segments of each M in A. Yeah, sorry for the typo. Sorry? A is a subset of X consisting of adequate structures. Next, we define the remainder points, which describes the overlap of models past their comparison point.
What do you mean by this, that N has access to the initial segments of each?
Yes.
Over here, A was an element of N, right?
So, you agree with me that this is finite, this A, and it lives in N by assumption. A is in N.
Yeah, that's what's missing.
Oh. Not A is in X, but A is in N. Yeah.
Oh,
Go
sorry.
ahead, go
So,
ahead, go
so,
ahead.
so the right
Now
assumption.
it makes sense. Yeah.
Now it makes sense. Thank you. Yes. Now I'm going to define the reminder points, which describe the overlap of modest past their comparison point. And if Mn is adequate, then the reminder points of n over m, denoted by R sub Mn, is defined as the set of those betas satisfying that either n is less than or equal to m, and beta is the minimum n which is above beta Mn, or there is a gamma m which is not in beta Mn, such that beta is the minimum of n minus gamma. This is a technical definition. The remainder is always finite, since otherwise there will be a common limit point of m and n, which is greater than the comparison point, but we have said that this is not possible. Given an adequate set A, we define the remainder R sub A, which is the set of all the possible reminders coming from structures living in A. Given S in omega 2 and an adequate A is said to be S adequate if all these reminders, they live in S, which is quite natural. And then finally we say that a finite set is said to be coherent S adequate if A is S adequate and A is symmetric style as per Mota. What does it mean to be symmetric? So imagine that we have two of these structures living in X. Then first of all we say that they are strongly isomorphic if and only if, of course, there is an isomorphism between these two structures, and this isomorphism fixes M intersection N, which means that if we have something in the intersection of M and N, then the image on their sigma is the element itself. Yeah? Yes, being the identity on M intersection N. And note that in such a case, M intersection omega 1 is equal to N intersection omega 1. So the exact definition of being coherent S adequate is, first of all, to be S adequate, and then satisfying these three rules describing symmetry. We say that if we have two structures in A which have the same height with respect to omega 1, then there is a unique strong isomorphism between these two structures. If we have a structure whose height with respect to omega 1 is smaller to the height of this structure, then there exists another structure containing this one and of the same height. That's condition B. Condition 3 is the dual of this condition, meaning that if we have two conditions of the same height and we have one living here, then the isomorphic image is also a part of A. Is that clear?
What is a strong isomorphism?
That means that you fix the identity. That means that you fix M intersection N. That means that if you have X in M intersection N, then the image of X is X itself. Now the rest of this talk is part of my. The rest of this first part of my talk is joint work with Kruger, and from now on we fix S subset of omega 2 such that S intersection those ordinals having cofinality omega 1 is stationary, and also we fix Y stationary in H lambda omega such that this Y is closed under isomorphism. What does it mean to be closed under isomorphism? Exactly the same idea. If I have two structures in Y and I have a third one here, then this is also the image is also an element of Y. And of course, by the Tarski-Baugh test, the club X is closed under isomorphism. The club S is the set of those elementary substructures which are correct with respect to the membership and with respect to the predicate Y, which cause a well order. Finally, we say that a poset P is said to be an SY coherent adequate type forcing if and only if its conditions are pairs XA such that X is a finite subset of H lambda. This is the approximation for an object that we want to add. A is a subset of Y and is coherent S adequate. This is a coherent S adequate set. 3 was 3 saying. Oh yes. But where is the eraser? Ah yeah. 3 is saying that imagine that we have a condition such that n and n prime, they are both members of the psi conditions associated to this condition. And imagine that you have something living here, x a, which is smaller than the original, which is weaker than the original condition. Yes, and it lives in one of these. Then the conclusion is that the isomorphic image is also a condition, and this is a weaker condition than the original one. This is I'm going to call this property symmetry. The fourth one is saying that imagine that you have a condition living in the intersection of a coherent S adequate set. Then there is a condition extending this, or there is a second condition extending the original one, such that all these models, they live in the part of the psi conditions, of the stronger one. So I'm saying this. Imagine that this guy lives in the intersection of a set of adequate is living in the intersection of a set consisting of adequate models. Then we can put all these models to A, and then we have a new condition. And
Kind of amalgamation, no?
sorry?
It's a kind of amalgamation.
Exactly, exactly. And finally, the last one is saying that, of course, whenever we have an M in A, then the part XA has to be strongly NP generic. And so for that reason, we have that all these coherent adequate type forcings, they add a lot of coherent reals because we have NP genericity. But what we're going to see is that we add only a small number of new reals. We add only omega-1 reals. Okay, from now on, lambda is going to be at least the successor of 2 to the omega. Of course, we continue with the assumption that the cofinality of lambda is at least omega-1. And imagine that this is the first, this is the Y first enumeration of the power set of omega, this enumeration of reals. So Y codes the relation set where set IM holds if and only if I is less than 2 to the omega and n is in the real Ri. And the first lemma is saying that if you have two structures in X, since they are very correct with respect to this predicate Y, then they have both the same reals. And this is because remember that if you have two structures of the same height, then they are isomorphic, yes? And imagine that the one you have one ordinal in 2 to the omega, then that we have the real R alpha, and then we have to see that this is equal to the real R sigma mn alpha. But that's going to happen essentially because both they are correct with respect to the predicate y.
Are you assuming the continuum hypothesis?
I'm not assuming anything. I'm assuming ZFC. And for the same reason, essentially for the same reason, and since imagine now that you have two structures. Imagine that you have two structures M and N. The height of N is bigger than the height of omega with respect to omega 1. We know that there is an isomorphic copy of M living in N. So all the reals of M are also reals of N. So for that reason, we have that any SY coherent adequate poset collapses 2 to the omega to omega 1 because we have omega 1 possible heights, and given two structures with the same height, they have exactly the same reals. And I don't know if I should continue explaining this part. Probably yes. Okay, so I'm going to give this lemma, but I'm not going to prove it because otherwise that's going to take a lot of time. Imagine that you have a predicate of h lambda, you have an element of h lambda, you have M and N living in Y, satisfying that set lives in both, in the intersection of M and N. M, N is coherent S adequate. So we want to find M and N in Y satisfying these two things. That set lives in the intersection. The pair M N is coherent S adequate. The structures are elementary with respect to the well order and with respect to the additional predicate R, and they are isomorphic. I should say strongly isomorphic. And there are alpha and beta, one in M and one in N, such that they are different, and the isomorphism sends alpha to beta. No, that's going to take a lot of time. So assume that you can do that. That you can always find this M and N, which are correct with respect to R, such that the isomorphism sends alpha to beta, and such that it contains set. Yeah. And using this lemma, we prove that if we have an SY coherent adequate poset, imagine that P forces that we have how many reals? As many as the successor of 2 to the omega. Then there is a condition Q below. There is a condition Q extending P and alpha different from beta, such that Q forces that F alpha is equal to F beta. So the sketch of the proof is as follows. Using the above lemma, we're going to use the above lemma. First define R, this predicate by letting that set I and M holds if and only if set is in P and set forces that Fin is equal to M. And now we fix two of these structures in Y, satisfying that P is in M intersection N. Mn is coherent, is adequate. The structures are isomorphic, and they are in fact strongly isomorphic. And there are two different points, alpha and beta, such that the isomorphism sends alpha to beta. And now we're going to prove that this condition. Well, I know that. Where's the eraser? So I have this P living in M and in N. And by one of the conditions of being coherent adequate pole set, I know that there is a condition extending P and having an M and N as side conditions. Yes? So this is this condition Q, such that M and N belong to the side conditions of Q. And now we have to check that Q, alpha, and beta work. And this is essentially a symmetric argument. We have that the condition has M and N as side conditions. The isomorphism sends alpha to beta. And here we're coding the real F alpha. And here we have the real F beta. Yeah. Now we have a strongly generic condition. So we are going to prove that F alpha n is the same as F alpha m for all for F alpha n.
F beta.
F beta n.
Be easy.
Yeah. So this is quite simple because we have said that M and N are side conditions, and they are warranting properness. So imagine that we want to decide this value here. So there is a because we have genericity for M, then there is a condition here deciding this value. Yes, but then remember that the forcing is symmetric. So it has to decide exactly the same value, and that happens for all possible naturals. So the conclusion is that these two naturals, they are exactly the same. And as a corollary, we have that we already know that any of these forcings collapses the continuum to omega 1. It forces CH. Forces that the successor of 2 to the omega in V is equal to omega 2. We have to see only the last part. And imagine that this is not true, that imagine that P collapses the successor of 2 to the omega. Then there is the successor of 2 to the omega has cardinality omega 1. Then this is possible to find a sequence of names. Then there is a sequence of names which P forces that there is an enumeration of omega 1 many distinct functions from omega to omega in order type, in this order type. But we have seen that this is impossible. And again, let us do a break. And I'm going to explain a little bit of history. Prior to this work, Ángel Mota proved that for any cardinal lambda of uncountable cofinality, the lambda symmetric forcing consisting of finite symmetric systems of countable elementary substructure of H lambda ordered by reverse inclusion preserves CH. And this forcing is one of the two forcings that they currently use in the first step of their finite support iterations for proving a certain forcing action with a continuum large. And as we have said before, a symmetric system is similar to a coherent adequate set, except that it doesn't have the structure of being adequate. And by a result of Miyamoto from 2013, the lambda symmetric poset, as well as any coherent adequate forcing on H lambda, adds an omega-1 tree with lambda many cofinal branches for any regular lambda. So we're adding Kurepa trees in all these forcing extensions. And certainly the CH preservation argument of Asperger and Mota slightly intersects the CH preservation argument of Kruger and Mota, but the format don't show how to force with psi conditions together with another finite set of objects to preserve CH. This may be an empirical evidence that Kruger's adequacy is crucial for this kind of construction, especially in the context of omega-2, when we want to add something to omega-2. Because in this way, we can compare elementary substructures of H omega-2. Okay, and as a corollary, we answer a question of Cy-Friedman, and for that, let me recall the following definition. Recall that a stationary set S of omega-2 is said to be fat if and only for every club of omega-2 S intersection C contains a closed subset with order type omega-1 plus 1. And as a corollary, we have, assuming CH, if S is fat stationary, then there is an SY coherent adequate P forcings included in H omega-2, preserving omega-1, omega-2, CH, and forcing that S contains a club. And please note that this requirement is the minimum that we can ask, since any club, since if we have a club, then this club has to have intersection with S at least omega-1 plus 1. I'm not going to give the forcing. Rather, I'm going to the second part of my talk. So, in the second part of my talk, I promise that I will add locally compact Hausdorff scatter space of high of width kappa and of high kappa plus plus for every regular cardinal. If you don't know that, that's okay, because I don't know neither all these topological definitions. But the good thing is that you can translate this problem in terms of partial orders. So imagine that we have a reflexive transitive and antisymmetric relation on kappa cross kappa plus plus. The poset kappa cross kappa plus plus is said to be admissible if and only if the following hold. Whenever you have alpha and beta is below alpha prime beta prime, then that means that beta, that implies that beta is an element of beta prime. For every beta in kappa plus plus and every alpha prime beta prime, this is the situation. So imagine that you have something here, alpha prime beta prime, and you have one beta which is below beta prime. Then there are infinite pairs here, such that this pair is below this pair. See, yes, see, whenever you have two pairs, then there is a finite subset V of kappa cross kappa plus plus called a barrier for these two order pairs, such that all the elements of V are below both, and in such a way that whenever you have something which is below these 2 points, there is one element of the barrier. If you have something which is below these 2 points, alpha, beta, yes, then there is an element of the barrier such that this element of the barrier is above this ordinal, above this pair. Yes, and the existence, in fact, is very easy to consider a topology here. The topology that we consider is by considering the cones generated by this order, and by declaring that these cones, they are clopens in the topology. So if we have that, then you can prove that you have a locally compact Hausdorff scatter space. Yes? And the theorem that we have here is that assuming GCH, for every regular cardinal kappa, there exists a poset p kappa such that p kappa is less than kappa close, and therefore p kappa preserves all cardinals at most kappa. P kappa is proper with respect to structures of cardinality kappa, and therefore p kappa preserves kappa plus. P kappa has the kappa plus plus chain condition, and therefore p kappa preserves all cardinals being at least kappa plus plus. Therefore we have the preservation of all cardinals. P kappa forces the existence of a kappa plus plus admissible poset. In order to describe this forcing, please let me introduce the following terminology. We will say that a set is of a small size if and only if its cardinality is below kappa. And a forcing poset P is proper with respect to structures of cardinality kappa if and only for every sufficiently large regular cardinal lambda for every elementary substructure M of H lambda of size kappa containing P and closed under small sequences, and for every condition P living in P intersection M, there is extension Q of P such that Q is MP generic. And a typical condition in this forcing notion P kappa can be described as a small approximation to the kappa plus plus admissible poset, together with a small symmetric system of structures of size kappa as side conditions. And so in order to be more precise, let me introduce the following notation. So remember that now we have structures of size kappa. Yeah. And therefore, it makes sense to consider the intersection with respect to kappa plus, and this is an ordinal in kappa plus, and I'm going to call this ordinal delta n. This is the height with respect to kappa plus. So I'm going to give the definition of being symmetric, a symmetric system in this more general context. Imagine that we have a predicate of H kappa plus plus. Let mu be a cardinal, and let Ni with I in mu be a small set. So mu has to be less than kappa, consisting of subsets of H kappa plus plus, each of them of size kappa. We will say that this set is a T kappa symmetric system if and only if the following holds. Imagine that, well, the first condition is saying that each of these Ni's is closed under small sequences, and Ni is correct with respect to the membership and with respect to T. There are elementary substructures of H kappa plus plus. Whenever we have two models with the same height, they have to be strongly isomorphic. Whenever you have two models, one of a smaller height, you have another having this height and containing this guy, and the fourth condition is saying that this is closed under isomorphism. And the fourth thing that we are going to consider is, first of all, fix a bijection between kappa plus plus and h kappa plus plus. This is possible because we're assuming GCH. Conditions in P kappa are sequences of the form, first, an approximation to the partial order, second, an approximation to the barrier function, third, that's going to be a symmetric system, and the fourth condition, that's going to be a subset of the symmetric system. So the first condition is saying that this is a small reflexive transitive and antisymmetric relation satisfying the first clause of admissibility. The first clause, remember, is saying that if alpha beta is less than alpha prime beta prime, then beta is below beta prime. The second one is saying that VQ is a barrier function whose domain is equal to the set of all pairs coming from the domain of this partial order. The third one is saying that this is a symmetric system. The fourth one is saying that delta Q is saying that omega Q is included in delta Q, where delta Q is our symmetric system. And the most important thing is that when something belongs to omega Q, that means that this is an active side condition, and therefore whenever we want to guarantee properness for these side conditions living in omega Q. Therefore, whenever you have two elements of the partial order which lives in N and N is in omega Q, then the barrier function is also an element of N. And I don't have time to describe this forcing. So as I mentioned before, David and Joan.
The extension.
Oh, that's the obvious one. Exactly. David and Joan, they introduced this forcing for kappa equals to omega. And the main difficulty, well, imagine that you want to generalize this idea from kappa equals to omega to any kappa. What's the main difficulty? The main difficulty is that you have to be able to define a barrier function. But if kappa is equal to omega, this is quite easy because all the conditions there are finite. So essentially, you can put all the barriers together, and you still have something finite. But in the context, for instance, in the context of kappa equals to omega 1, then your approximation to the partial order is for instance, something countable. So how do you amalgamate two different orders in order that you have finite barriers? Thank you.
Okay, questions? How do you do it?
Yeah. What's the trick?
Well, the thing is, for instance, imagine that we want to argue properness. So you want to argue properness for a certain model n. So you put n in the active part of a condition, yes, and then imagine that you extend this forcing. You have here some elements of the partial order that probably it doesn't live in N, but of course this approximation is small. So there is something very by correctness of N, there is something very similar here. So imagine that the order type imagine that the order type of all these guys is a certain number pi. Pi is of course below than kappa. So by correctness, we have something very similar here. We have an approximation to the partial order also of type pi, and in such a way that there is an isomorphism between these elements here and these elements here. And now we have to amalgamate these two partial orders. Imagine that this is the second partial order, and this is the first partial order, the partial order that we can see in N. So we have, of course, some amalgamation lemmas for partial orders. This is quite technical. So the main idea is amalgamating partial orders and using the idea of you have regressive functions. We are not regressive here in this context. We are progressive. If you have progressive means that f alpha beta has to be equal to. In general, we will have access to this coordinate alpha because it lives in kappa, but probably you don't have access to this coordinate beta, which lives in kappa plus plus. So this beta has to be, the image has to be alpha beta prime, where beta prime is at least beta, and it has to fix, of course, it has to fix the intersection of these two partial orders. Using this isomorphism, with some work, you can amalgamate everything.
More questions?
In his original work, Scheller used the delta functions to guarantee the CCC of certain forcing. Is it true that, or not, it's unknown, that your forcing also introduced a delta function for higher cardinals?
Sorry, I don't have any idea of what a delta
Okay,
function is.
then you just forget about that. It's too complicated somehow.
Yeah, that's why I don't know.
Comments?
Can you do omega over 3?
Not yet.
How about alpha bigger than omega 2 but less than omega 3?
Oh, I haven't.
This is usually not so, easy to go from kappa to any alpha less than kappa plus. In this case.
Yes, in fact, Bill say that most probably we are very close. We are very close to also to this result.
Do you think you can
think,
do it for all
exactly.
alpha of size?
Yep.
Kappa double.
Yeah.
Comments? No? Okay. Now let's thank Miguel Ángel again.
Thank you.